Okay, the standard hydrogen electrode, page 88, 88. Okay, the standard hydrogen electrode is also referred to as the SHE, which is kind of fun. Could you close the door for us back there, please? Thanks. There we go. All right. Now, the scientists use this cell for this half cell for reference. For all other half cell potentials. So here's the reaction at the SHE, and if you actually look on your data pages, it's the one that is in the very middle-ish of the table. So if you look, here's our table. You see we have 3 gray lines. The middle gray line, what's the middle gray line? See, we got 1 gray line, 2 gray lines, 3 gray lines. What's the middle gray line? Hydrogen. There's our hydrogen. Is good? You're right. All right. Page 88 for those people who just came in, page 88. So you'll notice that the E0 reduction, what does that mean? What does E0 stand for? The standard, the E0 red is the standard reduction potential. And when it says plus 0.00, what unit are we referring to? What is the unit? Volts. So if E0 of reduction is 0.00 volts, what is the E0 oxidation for H2? So if we're going, what if we're going backwards? What if we're going from H2 and we're forming 2H plus 2 electrons? It is still 0 because the oxidation potential on one line is the opposite of the reduction potential on the same line, and the opposite of 0 is still 0. Okay. What does it mean to have a standard that we use as a reference? Well, let's consider temperature, which is a scale we are really familiar with. What is 0 degrees Celsius? What are we referring to? That is the freezing point of water, and so it is a convenient temperature to use as a reference point. There's no reason to set 0 at the freezing point of water other than that it is convenient. Yes? Is 0 degrees Celsius an absolute value? Is 0 like really 0? No, because we can go below that. We have negative values, yes? So Celsius scale is not an absolute scale. It is a relative scale. Things above the freezing point of water have a positive value. Things below the freezing point of water have a negative value. And similarly, when we are looking at the E naught of the standard hydrogen electrode, the She, that is also not an absolute value. We picked it out of all the reactions because it's a nice simple reaction. Okay, 2H plus 2E minus gives you H2. Like, it's not big and complicated. We don't have O's and H2O's everywhere. But it also falls, in terms of its potential, right in the middle of most of the other reactions, right? So we've got like a nice sort of central value. Any substance that is a stronger oxidizing agent than H plus, what can you say about its reduction potential? It will be positive. And a positive E naught means it is what? Never mind. That's going to be a delta E naught. Pretend I didn't write that. Bye-bye. Okay. Any substance that is a weaker oxidizing agent, because remember, on the left-hand side of the table, what are we looking at? Oxidizing agents. Okay, so everything on the left-hand side of the table is an oxidizing agent. So if I was to go to my hydrogen here, copper 2 plus is higher up than H plus. Therefore, on this particular scale, that means that copper 2 plus is better at getting, is it better at getting oxidized or better at getting reduced? Think about that. Compare copper 2 plus with H. Why do they put the little button that makes it erase right where you would hold the pen? Like, it's driving me crazy. I have to take it home. I've done it with my other pens. Like, I put like a little foamy around it so my hand wouldn't accidentally touch it. It just sort of right anyway. But I'm like, why? Why would you do that? You could put it up here. You could put it up here. Who holds a pen up here? Nobody holds a pen up here. Do you guys hold your pen up here? No. Down here. Where did it go? Sorry. Anywho, is copper better at getting oxidized, copper 2 plus, better or worse, or better at getting oxidized or reduced than H plus? Everybody should be able to tell me. Reduced, thank you. And that is because copper 2 plus is a stronger what? Yes. And because it is stronger than H2, you'll notice that its E naught reduction is positive. Now let's take a look at nickel 2 plus. Nickel 2 plus is below hydrogen, therefore is it better or worse at getting reduced than hydrogen? It's worse at getting reduced. It is a what kind of oxidizing agent? Weaker oxidizing agent, and therefore it has an E naught reduction equal to negative 0.26. Okay, all the values on this table are reduction potentials. E naught red. Yes. Sure. Okay. Better at taking electrons. Yes. All right, let's go watch this little presentation here, and then we'll fill in the blanks. Here we go. It's not Tyler. Tyler doesn't do the she. Sorry. We have to hang out with Mr. Murray Green.
The standard hydrogen...
Now, I'm just going to warn you. He's British, and British use moles per decimeter cubed instead of moles per liter. Because a decimeter cubed is a liter. They also use kilopascals instead of atmospheres, but AP uses atmospheres. So 1 atmosphere is approximately 100 kilopascals. Okay, here we go.
Hydrogen electrode is used to determine the standard electrode potential of a half cell.
Oh, it's muted.
The standard hydrogen electrode is used to determine the standard electrode potential of a half cell. By definition, standard electrode potential is the voltage measured, or EMF we can say as well, when a half cell is connected to the standard hydrogen electrode. The standard hydrogen electrode is occasionally also called the standard hydrogen half cell.
Are we still sped up? No, we're normal. Okay, good.
Exactly the same thing. And for the most up-to-date version of any definitions mentioned in this video tutorial, please check out the video description, where you'll also find other links to further content from A-level chemistry. Let's take a look at what the standard hydrogen electrode is made of. Our apparatus needs to represent both sides of this equilibrium. To represent the H+ ions, we're going to use a 1 mole per decimeter cubed solution of hydrochloric acid.
Okay, so what do we have here? We have what would we use for the unit here? Moles per liter, so molarity. So 1 molar. Why are we using 1 molar? Because that's the concentration. But why did I choose 1 molar as the concentration? Pardon me? No. Take a look on your reduction potential table, please. And if you don't have a table, feel free to come and get a table. You will want to refer to one today. Why are we using 1 molar? Because that's what the table uses. Standard conditions are 1 molar. If you change the concentration, the voltages will not be what is given on that table, okay? Voltage, the E naught values are all dependent upon concentration, just like reaction rate is dependent upon concentration, things like that, okay? So has to be 1 molar solution because otherwise it's not at standard conditions. Now, what do you notice about the H2? What temperature is it at? This is our gas. 298 Kelvin. Do you know what that is in Celsius? That is 25 degrees Celsius. What's special about 25 degrees Celsius? Yes? It's the other requirement for standard conditions. Yes? At standard conditions, it must be 1 molar. It must be 298 Kelvin. And finally, they should actually be using... Actually, maybe it's the 1 atmosphere that's off, but 101.3 kilopascals is equal to 1 atmosphere. So I'm not sure whether we're rounding the 1 atmosphere or whether we're rounding the 100 kilopascals. We're just going to say close enough. Yes? So if you were in Britain, you would say standard conditions for a gas are a partial pressure of 100 kilopascals. Here we're going to say a partial pressure of 1 atmosphere, because we are working with the College Board, who are American, and Americans have a somewhat dicey relationship with the metric system. Okay.
The hydrogen gas we're going to use must be at 100 kilopascals of pressure and 298 Kelvin to maintain standard conditions. Since there is no solid metal in the half equation, we must use a platinum electrode. Platinum is used because we need it to transfer electrons, and also it's selected because it's unreactive, we can say inert, so we don't need to worry about any alternative reactions taking place.
All right, why did we choose platinum for our electrode? Tell your partner, why did we choose platinum for our electrode? Okay, what's one reason we chose platinum and not, say, iodine, which is also a solid? Yes. Number 1, it's unreactive. Okay, platinum is a good choice for unreactive. Some other good unreactive things are, can anyone think of another metal that is very unreactive? We use it for jewelry a lot because it does not tarnish. Gold. Would silver be good? No, because silver tarnishes. It is reactive, right? So it's gold and platinum are really good metal choices. Now, those are quite expensive. Can you think of another inert substance that's not a metal that could be used as an electrode? Maybe one we talked about the last couple days. Graphite, yes, a carbon electrode. We could use a carbon electrode as well. However, platinum is really conductive. So if we can afford platinum, we're going to use platinum.
As mentioned before, the standard hydrogen half cell is the reference standard to which all other half cells are compared to. We have to do this because we are unable to measure the standard electrode potential of a half cell all by itself. So by
Did that make sense? We have to, in order to measure a potential, we actually need to have both half cells. Because if you just have one half cell, is anything going to react? No. If you've got an oxidation half cell, it's going to sit there and go, I would like to give my electrons to someone, but I ain't got nobody to give them to. So you have to have it partnered up with something else. If it's not partnered up, you cannot measure its voltage because there's no reaction. So when finding the standard potentials, we're always going to partner up our unknown substance with a hydrogen electrode so we can compare it.
Finding the standard electrode potential of the hydrogen half cell as 0.00 volts, we can then compare the tendency of all other half cells to donate or accept electrons to the tendency of the standard hydrogen electrode.
If you just came in, we're on page 89.
And then report this as a positive or negative voltage value. Let's look at some setups to explain this. For consistency, and to allow us to assemble an electrochemical series, the standard hydrogen electrode should always be placed on the left-hand side.
On which side should we always place the standard hydrogen electrode? On the left-hand side. The reason for that is because the voltmeter is set up so that the left-hand side should be attached to the anode and the right-hand side should be attached to the cathode. That's how a voltmeter works. So if you were to put this on the right and this on the left, you would confuse the voltmeter. Yes? Or you'd have to cross your wires. It's just to do with the way the voltmeter is set up. Yes? Pardon me? If you flip it the other way around, it will be negative, but that's not going to give you the potential shown on your chart. Yeah? So that's why when we're using the hydrogen electrode, we always make sure it's on the left so that we're going to get the correct sign for our E naught, okay, for the reduction potential.
This way, the sign and value of the reading on the voltmeter can be allocated as the standard electrode potential of the other half cell. This is the apparatus necessary to record the standard electrode potential of the copper half cell. Here you can see we have the standard hydrogen electrode on the left and the copper half cell on the right. The copper half cell represents both sides of its half equation equilibrium by having a copper solid metal electrode placed in a solution of copper 2 ions. The voltmeter, as you can see, reports a value of positive 0.34 volts, and this is then assigned as the standard electrode potential of the copper half cell redox system.
So if you look on your chart, what is the potential recorded there of Cu2 plus 2 electrons gives copper? Look on your standard chart there. And what is it? Shockingly, it is positive 0.34 volts. I would like you to get in the habit of when we are referring to volts, of always putting a positive sign in front of something that's positive. Just like for oxidation numbers, if it's a positive oxidation number, you're going to put a positive. If it's negative, obviously, you're going to put a negative. But don't forget your positive signs. And while we're here, what would be in this tube here? Tell your partner, what would be in that salt bridge?
Yes, you just have ions on their own.
Okay, what's in the salt bridge?
Ions.
Ions. What kind of ions? Positive and negative. Okay. And what state are they? Aqueous. And what kind of characteristics should these ions have? They should be chill. Absolutely. You don't want them precipitating with anything. You also don't want them to be electrochemically very active. Yes, because you don't want them to go and migrate into a half cell and start reacting instead of one of your target ions. Yes? So if we just pause for a second here and go to our table. Where's our table? There it is. One of the reasons that we use potassium, K+, in the salt bridge, take a look at that potential for potassium ion to be reduced. How thermodynamically favorable or unfavorable is the reduction of potassium? Negative 2.93 volts. So the reduction of potassium is very thermodynamically unfavorable. So it's a good choice for using in your salt bridge. Sodium is also a good choice, but it's not quite as good as potassium. So often we will just choose potassium in case we happen to have some calcium or some strontium or some barium. Okay? Now we will often use, for our anion, we also want something that is going to be soluble with most things and electrically unreactive. Very often a good choice is going to be NO3. What's one good reason for NO3? It doesn't precipitate with anything. And if you don't have any acid around, if you have not acidified your solution, can NO3 get reduced? No. Do you see how those reactions of NO3 being reduced include H+ ions? If you don't have a source of acid, if you don't have more than, just the slight H+ from the dissociation of water, you're not going to get a reduction of NO3. Is good? Okay. Back to our video. Yeah. Yes? The electrons would be flowing that way. Is that, yeah, that's what you thought? Yeah, okay. Sorry, I have to backwards for my brain. Oh my goodness, Mr. Look, a student of his just gave him some goggles. They're upside down goggles. Oh, yeah. So they flip the world upside down. They're kind of fun. If you ever get a chance to try them, I would totally do it. They're interesting. Okay.
Now, with some further labels, we can actually see that this copper half cell is the cathode, the positive electrode, and the hydrogen half cell is the anode, the negative electrode. These roles can be allocated using the standard electrode potential values once we know them. Since we now know the half cell for the copper has a more positive standard electrode potential, we can understand that it has a greater tendency to accept electrons than that of the hydrogen half cell in this particular pairing. We could also say that the copper redox system position of equilibrium is further to the right than the hydrogens. Looking at the very top labels, the direction of flow of electrons is from anode to cathode, aka negative electrode to positive electrode.
Does that ever change? Do electrons ever flow from the cathode to the anode? I want you to think about that for a second. Think about what process takes place at the anode. What half reaction occurs at the anode? Oxidation or reduction? Oxidation, because anox paired. Cathode reduction. Anode oxidation, cathode reduction. So you have oxidation. What is oxidation? Oxidation is losing electrons. And so if the anode is undergoing oxidation, the anode is losing electrons. And so the electrons are coming out of the anode. And then they go into the cathode. Therefore, which direction do electrons have to flow? From the anode to the cathode. A nice way to remember that, if you don't want to work through that whole logic chain every single time, electrons flow in alphabetical order from A to C. Okay? Anode to cathode. Yes? What about the salt bridge? Yeah, what's happening in the salt bridge? We're going to get ion movement in the salt bridge. Which direction will our anions move? Will they move towards the hydrogen electrode or the copper electrode? Which way will the anions move? Towards the hydrogen electrode, because the hydrogen electrode is the, or actually I should say the platinum electrode, because the electrode itself is platinum. The platinum is the anode. And where do anions move? Towards the anode. That gives us a complete circuit of negative charge. Electrons flow from anode to cathode, and then the negative ions continue the circuit, moving from the cathode to they move towards the anode. Which way do the cations move? Towards the cathode. That's why the anode and cathode have their names. It's because of the migration of the anions and cations.
And the salt bridge that we've got labelled up in the middle completes the circuit by transferring ions, not electrons. That's a common mistake. Next up, we have this apparatus for measuring the zinc redox system's standard electrode potential. So here are the half equations we need this time. Once again, we have a solid zinc electrode in a solution of zinc 2 ions as represented in the half equation in a very similar way to the copper half cell in the previous example. The standard hydrogen electrode is on the left, and this time our voltmeter reading is a negative 0.76 volts. This value and its sign is allocated as the standard electrode potential of the zinc redox system.
Is that a let's see, is that a reduction potential or an oxidation potential, the negative 0.76 volts? Think about it, chat with your neighbor. Okay, now remember, we hook up the voltmeter when we're measuring an electrode versus the She, versus the standard hydrogen electrode, with the hydrogen on the left, so that we will get the correct sign for what kind of potential. Our table is a table of standard reduction potentials. So when you hook it up this way with the hydrogen electrode on the left, you will be measuring the reduction potential of the element, whatever it is on the right-hand side. If you were to hook it up the other way, if you switch the She and the zinc, you would be measuring its oxidation potential. Okay?
The zinc half cell here with this final set of labels is actually clearly labeled as the anode this time. So that's different from the previous example, as we see a different direction of flow of electrons. The negative value on the zinc standard electrode potential informs us that the zinc position of equilibrium is actually further to the left than the redox system of the hydrogen, and that the zinc has a greater tendency, therefore, to donate electrons. If I wanted to create a functioning cell with a positive cell potential here, I would actually need to move the standard hydrogen electrode over to the right-hand side. But for recording these standard electrode potential values, we keep it on the left for consistency.
Okay, now just before we move on, at the bottom of page 91, we have a little question. What is going to happen to the pH near the platinum electrode as the cell operates? Bottom of page 91. So platinum is our cathode, yes? What process takes place at the cathode? Reduction. Red cat. Okay, red cat.
It's always the one she does.
So cathode reduction. Both are consonants. C and R are both consonants, so those two go together. A and O are both vowels, so those go together. So anode oxidation, cathode reduction, anox cared or anox red cat. Okay, so many different ways to remember that one. The cathode is where reduction takes place. So if we're looking, are we going forwards or are we going backwards? We are going What half reaction is happening in the forward direction? That's reduction. And the backwards is oxidation. And so we are going in the forward direction. What is happening to the amount of H plus? It is decreasing. Therefore, what is happening to the pH? The pH is increasing. This is the kind of question that could show up. They do like to ask about pH near an electrode if there's any sort of reaction involving hydrogen, either as a reactant or a product. Okay? So the platinum electrode is the cathode. Reduction takes place at the cathode. Therefore, the shear reaction is 2H plus 2 electrons goes to H2. Therefore, H plus is being used up. Therefore, the concentration of H plus decreases. Therefore, the pH increases at the platinum electrode. Is good? Okay. Now the answer is actually on the next page and it's all written down for you, so we'll just leave that. We are now going to go to just see what it really looks like because that diagram doesn't look much like real life. So we have a little video, okay, that's just, it's a quick one.
Are the oxidation and reduction potentials absolute values?
Are the oxidation and reduction potentials absolute values? No. What are they instead? They're not absolute. They are relative.
The truth is, they are not. They are relative. In order to assign them a standard value, it is necessary to compare them to the potential of a reference electrode, the standard hydrogen electrode. Today, you will learn all the details of this fascinating electrode. Our objective is to study the design of a standard hydrogen electrode. A standard hydrogen electrode consists of a platinum plate.
Oh, by the way, you don't need to memorize how this is constructed. You would at best have to draw a schematic diagram, and I don't think that is likely. But it does help to kind of see what it actually would look like in real life.
Coated with platinum black. The platinum plate is connected to a platinum wire, which is sealed in a glass tube. A little mercury is placed inside the glass tube and a copper wire is dipped in it for external contacts.
So the mercury is just to provide, because mercury is a metal, and because it's a liquid, it will just, form, it will take the shape around the two electrodes. So it provides a connection between the copper wire and the platinum wire. Yes?
This glass tube is enclosed by an outer jacket having a bell-shaped bottom. This outer jacket also consists of an inlet for hydrogen gas. It is dipped in the solution of 1M hydrochloric acid. This completes the assembly of a standard hydrogen electrode. The standard hydrogen electrode potential is considered to be 0 volt at standard conditions, which are 1 atmospheric pressure, 25 degrees Celsius temperature, and 1M HCl solution.
Okay.
The standard hydrogen electrode acts as a reference electrode and it is used to measure the potential of other metal half cells, such as silver half cell, where it acts as an anode, and zinc half cell, where it acts as a cathode. To summarize, we have learned a standard hydrogen electrode consists of a platinum plate coated with platinum black. The platinum plate is connected to a platinum wire which is sealed in a glass tube. This tube is covered with an outer jacket which is dipped in a 1 molar HCl solution, and how it can be used as a reference electrode to measure the potential of other electrodes.
Okay,
So the standard hydrogen electrode.
we're just going to stop her there because I think we've gotten all we can get out of that one. And we're going to go back here because now we want this one. This isn't, yes.
Specify the color of the platinum then for it.
No. Yes.
Like, no black.
I don't know. Probably just because platinum is expensive and you probably want to make the bulk of your wire out of copper. That would be my guess, but I could be wrong. Honestly, do you need to know how it's made? No, you can just be like, there's a wire, there's platinum at the end, yay. Yes, you need to know that there's a glass thing around it. Why do we need that glass thing around the wire and the electrode? Oh. Pardon me? Because you have a gas. How else are we going to get hydrogen gas to go, like if it's coming in here, how are we going to get it to go down if there's no container? It would just be like, right? It would just go away. It would not go down into the solution. So we need that bell-shaped glass to direct the hydrogen so it bubbles into the solution around the platinum. All right. Are you interested in seeing what it looks like in real life? Yeah. Okay.
Welcome to this video on the standard hydrogen electrode. In order to produce this electrode or half cell, we need to generate some hydrogen gas. And so we've got in this flask on the left some sulfuric acid reacting with zinc granules. It's got some copper sulfate in it to make the reaction faster. You can see the hydrogen gas coming out of here at the top of the flask, and it's passing through the orange tube, through an aspirator containing potassium manganate 7, which is just oxidizing any sulfurous gases that have been produced, and then over across through the pipe and now into the main setup, which we can see here. In the beaker here we've got some 1 mole per decimeter cubed hydrochloric acid, and then bubbling into the beaker through this pipe at the top is some hydrogen gas at a pressure of 1 atmosphere. And inside this housing we've got a platinum wire, and at the bottom we can see some porous platinum. That's going to be taking the electrons out of this half cell in a moment. In order to use the standard hydrogen electrode.
So do we feel that's okay? We're good? We've seen it? All right. Excellent. Okay, we are now moving on to page 93. Cell potentials. This should be easy for you because you watched a video about this last night. Okay? And if you didn't, then you need to go back and watch the video. All right. So when we are doing a potential voltage of an entire cell, including both half cells, most of the time we won't have the standard hydrogen electrode. So we have to take into consideration both the reduction potential of the cathode and the oxidation potential at the anode. Does that make sense? Okay, good. So if we have here, we have zinc is at a certain potential, and copper is at a certain potential. And the potential difference between those is 1.10 volts. Cobalt, on the other hand, is a smaller difference than zinc. Or sorry, than the copper from zinc. Does that make sense? Okay, so which one will produce a greater voltage? This is the potential difference. First one, okay, it's pretty obvious. It produces a greater difference. So if we were to go to our data pages and I were to say we are going to make a cell, get rid of all this. We're going to make a cell with nickel and chromium. Okay? That right there, that difference right there between those two values, that's going to be the reduction potential of the cell. So what we're going to do is we're going to take the reduction potential of one of them and add it to the oxidation potential of the other one, or we can subtract the reduction potential, and we'll get into that in a minute. But let's just pick another one here. Let's say instead of using nickel, I used lead with the chromium. Which one would give me a larger E0 cell? Lead, okay? Because you can see what's the difference? The difference is much bigger. So that's what we're doing when we're calculating the potential of the cell. We're calculating the difference between those two values. And if you look at this one, we're looking at the difference between negative 0.26 and negative 0.74. So you could just do a subtraction there, and that would give you the difference. I'm going to show you two formulas that you can use, or you can also logic your way through it. You can be like, oh, if I look on my chart, the difference between those two is going to be a subtraction. Yes? Okay, so the cell potential depends upon three things. It depends upon the identity, it depends upon the concentration, and it depends upon the temperature or pressure if you've got a gas. And so just reminding yourself, tell your partner what are the standard conditions for an electrode. For 25 degrees Celsius. 1 molar. 1 atmosphere. Okay, good stuff. So actually we have like a little problem here. Let's say that we have a zinc copper half cell. If you remember, what is this guy here? Is that the anode or the cathode? If we're using line notation. That is the anode. And this guy over here is the cathode. Okay. And in the reaction, zinc is turning into zinc 2 plus, copper 2 plus is turning into copper solid. So here's our cell, and we have 1.10 volts. If instead of using copper, we then use cobalt, we get 0.51 volts. Using that information, I'd like you to see if you can puzzle out what the E0 cell would be for a cobalt copper half cell. Or sorry, not half cell, full cell. See if you can think your way through that one. Don't look on your chart. You should be able to figure it out from this alone. Initial what with who? Initial cell voltage is E naught cell. That is standard conditions, because what will happen is over time, your reactants will get used up, and so the molarity will no longer be 1 molar. Yeah? Yeah. You don't look at your chart to do this one. You can do it just from here. Because I might give you something that's not on your chart, like X, Y, and Z. Yeah? Yeah. Absolutely. I would love that. That'd be great. That might get you started. Maybe. Are you kind of with me so far? Okay, so we have the difference in reduction potential between the copper and the zinc is 1.10 volts. The difference in reduction potential between the cobalt and the zinc is 0.51 volts. So what if we made this our anode and we made this our cathode? How many volts is that going to be? 0. What? 59. And there's no particular way of I don't think there's a method for doing that. I think you just got to think your way through it. Okay?
I had to write it. I can't do facts in my head.
I can't either. That's why I have to draw a picture and use my calculator.
Yeah.
Both of them. Okay. So here are some ways that you can calculate the potential. So you can use a reduction potential and a reduction potential. So you will use the reduction potential for the cathode and the reduction potential for the reaction happening at the anode. And if you subtract those, you will get the potential of the cell. Is good? Okay. Let's take a look at what that would look like on our chart. If we have a nickel chromium cell, yes? This is the reduction potential of nickel. And nickel is nickel the anode or is nickel the cathode? If I've got a nickel chromium cell. What is nickel better at doing? Is it better at getting reduced than chromium, or is it better at getting oxidized than chromium? So is nickel better than at getting reduced than chromium, or is nickel worse at getting reduced than chromium? Better, because this is negative 0.26. This one is negative 0.74. So which one is thermodynamically more favorable? Is a more negative value more favorable, or is a less negative value more favorable? Less negative. So nickel is going to get reduced. Okay? So in fact, anytime you have an electrochemical cell, whichever reaction is on the top, whichever half reaction is on the top, is going to be the cathode. Yes, it'll be the reduction, so it goes forward. Okay? And whichever one, if we're comparing these two, and we say, let's just get rid of this here. What is the E0 oxidation of nickel? Positive 0.26. And the oxidation potential of chromium is positive 0.76. So who is better at getting oxidized? Oh, huh? Oh, 74. I just can't do numbers. Yes, thank you. Who is better at getting oxidized? Chromium is better at getting oxidized. So the nickel reaction is going to proceed from left to right. The chromium reaction is going to proceed from right to left. So this is the top reaction will always be the reduction for an electrochemical cell. The bottom reaction will always be a oxidation. And I don't know, this is how I thought about it in my head when I was in high school. I always thought electrochemical cells go like this. They give off that amount of energy, right? They release that amount of energy as they fall from higher potential to lower potential, and then it goes backwards. So it's like, so that's an electrochemical cell. Does that make some kind of sense? Okay. So electrochemical cells go like that. And whatever the difference is between those two is the E0 of the cell. So in our example, we had E0 cell equals E0 reduction at the cathode minus E0 oxidation at the, or no, sorry, E0 reduction at the anode. My apologies. Yoav. You guys are hilarious. So please tell me, what is E0 for reduction at the cathode? What value should we be writing down for E0 reduction cathode? Oh my God, you guys are killing me. What's the reduction potential at the cathode? Negative 0.26. Okay, so we're going to write negative 0.26, and are we going to put a unit with that? It doesn't have a unit? Volts, thank you. Okay. Minus, what is the reduction potential for the anode? Negative 0.7 6 volts, which means that we're subtracting a negative value, which means we're going to get what kind of a value? Positive value. Which is positive 0.48 volts. Does that track with this being an electrochemical cell? Should an electrochemical cell have a positive voltage? Yes. It should be producing energy. Remember, electrochemical cells are batteries. They will provide energy to other things. Yes? Okay. Did you have a question? Yes, you're right. I keep doing it here. 7.4, which would make this 0.46. There we go. Thank you. Okay. So that's formula number 1. Formula number 2, this is the one I like, but it doesn't quite make as much sense if you're subtracting to find the difference between the two. But for some reason, this one just makes my brain work better. So you pick the one that makes your brain work better, okay? You can also find it by taking the E0 reduction at the cathode and then adding the E0 oxidation at the anode. Because remember, the oxidation potential is the opposite. So subtracting a reduction potential is the same as adding the oxidation potential. So pick which one you like best. I always like thinking what's actually happening. I have this reduction, so I'm going to write its reduction potential. I have this one, which is oxidation, so I'm going to write its oxidation potential. I'm just going to smash those two together, and there we go. So let's pick another one on our data pages. Let's do lead and copper. Lead and copper. Just look at your chart, tell your partner quickly, who's the cathode? Who's the copper? Who's that? Oh, whoops. Who's the cathode? The cathode is copper. Why? Because it is higher. So which direction is that half reaction going? Right to left or left to right? Left to right. That's our reduction. And then that means that lead is the anode. And which direction does that mean its half reaction is going? To the left. And if we wanted to calculate E0 cell, we still take the reduction potential at the cathode, but now we add the oxidation potential at the anode. What is the reduction potential at the cathode for this cell? It's going to be positive 0.34 volts. And we're going to now add, what is the oxidation potential for your anode? Positive 0.13 volts. And so you end up with 0.47 volts. Is good? Yes. Yeah. Okay, for homework, let's see what we want you to do. Let's make sure that you have done Did you do pages 80 to 82 or 80 to 81? No, that's not it.
No, why would you say that? That is a lot, bruh. It's not. I need to stop.
We need to get through this course, so yeah, I'm gonna just find out what we need to do here. Okay, hang on. I don't know which of these you've done. So I'm just gonna write them all down. You do the ones you haven't done.
Go.
Page 98. I know you've done such. Which ones of these have you done already? You've done this already? Okay, so that one's gone. Did you do 80 to 81? Some of you have, some of you haven't. Do 80, 81, and then do page 98. If you don't get all the way through 98 because you haven't done 80 and 81, then that's okay. You'll just do that next day. Okay? Is good? Awesome.
Someone has a little speech.
Godwin has a little speech. Here we go.
So this Friday is Phone Free Friday, and we'd love for you guys to participate. We've had like 2 Phone Free Fridays so far, and it's basically the same thing. It will just be in the mornings, you come in the commons and you grab an envelope. You'll have your name on it and they'll seal it for you. At the end of the day, you bring back that envelope undamaged, and you'll get an entry into a draw. For this Phone Free Friday, we have 7 grand prizes.
Ooh.
So there would be 6 $20 Logi gift cards, and then 1 $100 PlayStation gift card. And just try Phone Free Friday and completing it, you'll get a candy. Just yeah.
Patty.
Just keep your envelope. You don't let nobody know.
Thank you, Godwin.
Wait, getting some.
Exactly. Every other just on like if you're there, you have
This is a reminder. Real 11 and 12. Have to be not picked up their tickets.
Hi.
TOC, you'd make more money?
It'll make the
No,
same.
it's at scale. It's at
Yeah,
scale
it's
up
the same.
to the max of.
Oh,
Actually, a little bit more because you don't have to pay the